All right. So we're going to look at our last example for today's lesson, which is a three-body system. So this is, not much different than what we've been doing, but just to show you that these forces, like any other forces, can be summed and can be applied to each other in net. So we're going to have to do a little bit of Pythagorean work. Not a big deal. You're going to do great with it. So let's take a look. So here we've got three different objects in space. Three large spherical asteroids in space, which are arranged at the corners of a right triangle ABC. There we go. Asteroid A has a mass of 1.1 times 10 to the 20 kilograms. B has a mass of 2.0 times 10 to the 20. And C has a mass of 4.0 times 10 to the 20. So they are getting progressively heavier, and the distances are laid out as we see. So we've got A to B is 5.0 times, this is 5.0 times 10 to the 10 meters. And this down here is, what did we say that was? 2.5 times 10 to the 10 meters. And then we said this has a mass of 2.0 times 10 to the 20. This has a mass of 4.0 times 10 to the 20. And this has a mass of 1.0 times 10 to the 20. All right, so there are masses. I always like to mark up the diagram. You certainly don't have to, but there we are. So determine the net force on asteroid A. It's not some big deal. You're just going to have to find the effect of B on A and the effect of C on A, and then you're going to have to add them together. So you can see that we're going to get two forces. So, first, okay, so we can find the force of gravity of B on A, and the nice thing is, because we're at 90-degree angles to each other here, it won't be so bad, right? So B is going to be pulling A up like this. That's the direction of that force, right? Remember that gravity always pulls. So B acts on A to pull it towards B. So there we go. So, no big deal. We know our equation here. It is just the force of gravitation, the mass of the two objects. In this case, that's the mass of B and the mass of A, divided by the distance between them, squared. And we know that there's 6.67 times 10 to the negative 11 newtons of force for every kilogram that is held a meter apart. And then, what are our masses here? Ooh, this is going to be a big old line. In fact, I might give myself a little bit of space to work with here. There we go. Well, the mass of B, we said, was 2.0 times 10 to the 20. And the mass of A, we said, was 1.0 times 10 to the 20 kilograms. Okay. And the radius between them was 5.0 times 10 to the 10 meters. And we have to remember to square that distance. And so we can find the force of gravity of B on A. And that is Well, let's plug these into a calculator, shall we? So force of gravity P on A is equal to 6.67 times 10 to the negative 11. I should just define that as G, but that's okay. In fact, why don't I do this? Why don't I take 2 seconds and set my equation up here. So G is 6.67 times 10 to the negative 11 newtons per kilogram squared per meter squared. And then the mass of B we said was 2.0 times 10 to the 20. The mass of A we said was 1.0 times 10 to the 20. The mass of C we said was 4.0 times 10 to the 20. And then the distance A to B is, we said, 5.0 times 10 to the exponent 10. And the distance, oh, it doesn't like D, but that's okay because we want, yeah, okay, there we go. And the radius, reminder of my diagram here, A to C, is 2.5 times 10 to the 10. All right, now we've got our variables all laid out. That's nice. Now we can say the force of gravity of B on A is going to be G MB MA divided by the radius between A and B. And there we go. Yeah, I'm happy with that. Oh, we need to square this down here. Ooh. Okay, am I happy with that now? I think I'm happy with that. Yeah, that looks pretty good. Okay. So I'm gonna do a couple things. First, I'm gonna lay out my, oh, I hate when it does that. I'll lay that out here. I like that. Okay, and then there we go. And of course, we like scientific notation more than we like that. So we'll say 5.33 5.336. We'll keep times 10 to the 6. Right, 1, 2, 3, 4, 5, 6. Oh, 7, 8 times 10 to the 8. Sorry, newtons. And we should give a direction because it's a vector, of course. So on y-axis. Okay, so there we go. So that is the first one. Now we can determine this. That's the vector we'll go for next. So second, we'll say this. We'll say, okay, now that we've got that, let's take a look at this vector. And again, we can say this is the force of gravity of C on A. And it'll be the same thing. It's just going to be the gravitational constant times the mass of C times the mass of A divided by the radius from A to C squared. Not going to forget to square it like last time. All right, and that's easy. We'd say that's 6.67 times 10 to the negative 11 newtons per kilogram squared, meters squared. Oh, meters squared per kilogram squared. How many times have I put that wrong? Probably too many. The mass of C is 4.0 times 10 to the 20 kilograms. And the mass of A, we said, was 1.0 times 10 to the 20 kilograms. And we're going to divide that by the radius between them, which in this case is 2.5 times 10 to the 10 meters. And we're going to make sure we square that. Okay, now again, let's actually calculate it. We can say F G C on A. And again, we can say gravitational constant, this time the mass of C, multiplied by the mass of A, divided by the radius of AC. And we need to remember to square it. And there we go. And so now we get, what did we get for that? 4.269 times 10 to the 9. Okay, and so now we can say force of gravity of C on A is 4.269 times 10 to the 9 newtons, and that's going to be on the x-axis. And now these are vectors, and you know how to add vectors. All right, you know how to add vectors. You've got this vector here. Or what colors did I use? I used purple and orange. You've got this vector here. You've got that vector there. And so our resultant vector, this one, we'll just be putting these two things together. And we know how to do the Pythagorean Theorem, right? So we know that we can just do the square root of a squared plus b squared. And we know that we can do the tan of, if we want to get that angle, A over B. Hopefully by now we are really comfortable getting the direction and angle from these things. So let's just do it. We can say the force of gravitational net is going to be equal to the square root of the force of gravity of B on A squared plus the force of gravity of C on A squared. And that will be equal to and there we go. So the net force is 4.3 times 10 to the 9 newtons. And so we can plug that in. And to get the angle, if that's the angle we're going to find, because A is going to be pulled basically in this direction, So let's find the angle off the y-axis. So that would be opposite over adjacent. So that would be C on A over, over B on A. So we can say theta is equal to the tan inverse of FGC on A divided by FG B on A. And with that, we can just plug it in, make sure we're in degrees, and we can say theta equals tan inverse, which they call arctan, of FG C on A divided by FG B on A. There we go. And we get 82.9 degrees, which means I probably should have measured off the x-axis, but that's okay. So we can say equals 82.8 degrees off the y-axis, or 7.1 degrees off the x-axis. And so our force of gravity net is equal to 4.3 times 10 to the 9 newtons, 7.1 degrees above the x-axis. And there we go. Not a terrible question. Definitely doable. There's a B part. The B part is trivial. The net force on B from C. The net force on B from C is not going to be, especially difficult. The only thing you'll need to do is calculate the distance between them. So the only thing that really makes this difficult, we need R, B to C. And so if we draw our diagram, or if we look at our diagram, we'll draw it. We know that this is 5.0 times 10 to the 10. We know that this is 2.5 times 10 to the 10. And so the question is, what's that? And to get it, it's not a big deal. Just Pythagorean Theorem, because it's 90 degrees. We can say the radius, or the distance from B to C, is just going to be the square root of 5.0 times 10 to the 10 meters squared, plus 2.5 times 10 to the 10 meters squared. And we get RBC being equal to 5.9 times 10 to the 10 meters. So that's good. But then we also need the angle, right? But we know how to do angles. So what angle do we want? We can measure off the x-axis. That probably makes the most sense. So we'll call that theta. And we can say theta is going to be the tan inverse of opposite over adjacent so 5.0 times 10 to the 10 meters divided by 2.5 times 10 to the 10 meters. So we're doing the arctan of 2 really, but that's okay. Theta equals arctan, which was which? We said RAB divided by RAC. And we get 63 degrees. Great. Again, you could just as easily measure it the other way and say 27, like that's fine. This is 63 degrees off the x-axis. Okay, and now we know the radius between them. Now to calculate the force is trivial. We just say, okay, the force due to gravity of B on C will just be the gravitational constant times the mass of B times the mass of C divided by the radius of B to C. And we have to square that. And let's do that. Oh, I did something horribly wrong. There we go. All right, and we should get 1 point, how many sig figs do we want? Just 2. So we should get 1.7 times 10 to the 9. And there we go. We got it. So we can say the force of gravity of B on C is just going to be 1.7 times 10 to the 9 newtons, and that's going to be 63 degrees off the x-axis. All right. Whew, a tricky one, but you guys did great. Hopefully that made some sense to you. That's it for today. Sorry again I'm not teaching this lesson live. I don't even realize the meetings I have coming